Hello and welcome back to another one of these A-level physics videos. Today we're going to be looking at the vector mechanics part of the mechanics section. So again, this will also help with the A-level mechanics, just as like an added little bonus. So with vectors, as we've said before, they are things that have a size and a direction, so things like acceleration, velocity, force, etc. So we've normally, up until now in GCSE for instance, we've been dealing with vectors that go kind of horizontally, vertically, but the key point here is that we always treat them in pairs, right? So they're either going up and down or they're going left and right. Now in actuality, if you think about real life, most of the time forces act at some angle theta to a horizontal, right? They don't always act, perpendicular to each other or just to the left, just to the right, up or down. So what we need to be able to do, and this is in A-level maths and physics, is we need to be able to break up these forces into components, okay? So what we can do here is I can break this force up into two perpendicular components. A component that goes to the right and a component that goes up. So just to explain this a bit in another way, this force here is acting, it has a mixture of components. A component that makes it go to the right and a component that makes it go up, which means the overall effect is that it goes up and to the right as a diagonal. Okay? Now the way we work this out is just using simple trigonometry, right? This is a right angle triangle. So if we have the hypotenuse and we want the adjacent side, we'll be using cos. So we know that cos theta equals f over the adjacent side, which means this side here is just equal to f cos theta. Okay? So actually that's the other way around. So a over f. Okay? Likewise here, you can show that it would equal f sine theta, because again we'd have sine theta equals the opposite side over f, and therefore you rearrange. And honestly, that's all there is to it. So you just need to keep in mind that when you're doing something like this is a skill that comes up again and again and again in physics and in maths. If you are going to be finding the resultant force of kind of forces acting on an object, you need to resolve them into perpendicular and parallel components. So for example, let's say we have a box, right? And there's one force that's acting directly to the right, let's say 10 newtons. And then we have another force which is acting up and to the left at 20 newtons. An angle of 30 degrees. If we were to try and resolve this force and work out the resultant force, I can't just do 10 minus 20, right? Or 20 plus 10 or something like that. Whereas normally, if I had, or in the kind of old way of doing things, my forces would always be acting parallel to each other. So then working out the resultant force is a trivial matter of doing, the difference between 5 and 10. And again, that would be if the right is positive. Remember, we took directions as positive in the SUVAT video as well. So my resultant force in this case would be -5, but I can't do that in this case. Why? Because I have two components. So I have to actually resolve this into parallel and vertical components, so two perpendicular components. So let's say if I take to the right as positive, my actual resultant force, if I'm just taking horizontal components into account, is going to be the 10 newtons here minus this adjacent point here, because as you can see, this is obviously going to be travelling to the left, and this is going to be travelling to the right. And if I had a force that was going down, then this component would be going down and this component would be going to the right. Okay. So then that would be adjacent, so that should be 20 cos 30. And again, just to illustrate that, we have that cos 30 should equal that adjacent side over the hypotenuse, which is 20. Okay? So then that's minus 20 cos 30. Okay? And then you can work out whatever that is. So if we get our calculators out, we have 10 minus 20 cos 30. I also need to check if I'm in radians mode. It looks like I am. So I need to change the angle into degrees, equals, and it gives me a negative number, sorry. So minus 7.32 newtons. So what does that mean? Well, 7.3 newtons, since it's negative, it's going to be travelling in this direction. That's my resultant force horizontally only. And then obviously you'd have to include the vertical component as well. So if we resolve this vertically, well, we only have one force, right? And that force, and if we take upwards as positive, because we only have one force, is just 20 sine 30, which we can work out. Which is just 10. I should have actually known that. I didn't actually read the angle properly. 10 newtons. So what does this mean? Well, the overall resultant force, the actual magnitude of it, if I were to work it out, is a vector that has two components. So to actually work out what the value is all you'd need to do is take the magnitude of the vector, which is adding them together and squaring them. Which again should make sense, because remember, we have a component of the force going this way and a component going this way. This component is 10, this component is 7.3, and whenever you're working out the resultant force, you're just working out the hypotenuse of that triangle. Like that. So all we're doing is adding the vectors together. If this doesn't make sense to you, don't worry too much, because we have got a couple of questions that are going to help out with this vectors topic, so don't worry too much. But again, with practice, this will become a lot easier. But in general, just expect that in physics and maths, we're going to be kind of resolving vectors into their perpendicular components. Okay, so that means the overall resultant force in this system is 12.4 newtons, acting to the left and up. Okay, so let's get started with some questions, shall we? So again, we have some multiple choice questions. Let's get started. Which of the following is a vector quantity? So, easy way to work this out. This is energy, and that's time. None of those are vectors, so that means momentum must be. And again, one way to work that out, if you're unsure, is to always look at the equations. So we have P equals mv. V is velocity, which is a vector, times by a scalar, so that must be a vector. Okay. Same with work done, it's force times distance. Well, it's not always force times distance, and then you also have kinetic energy, but energy is not a vector because it doesn't have a direction, right? I don't say I have 10 joules downwards, do I? But I do say with momentum I give a direction. Next is an object is in equilibrium under the action of three coplanar forces. So coplanar just means they act on the same 2D sheet, F, R and W. The diagram below shows the forces F and W. The angle between them is 90 degrees. Which row shows the correct magnitude of R, where R is the resultant force, right? So, all we need to do is, if we draw these forces together, right, and it also gives us the values here. Now, for this object to be in equilibrium, its resultant force needs to be 0. So basically, we're going to join this line up here to go back, because this kind of closed system here will have a net force of 0. The other way to look at it is, if I were to draw this object out, its weight is going down by 4.5, and it's being pulled to the left by 6.2, right? So that's W and that's F. For it to be in equilibrium, we need to cancel out those forces. So one component is going to be to the right by 6.2, and the other component will be going up by 4.5, right? Because for there to be no overall force, there needs to be a force that counteracts W going down and F going to the left. Okay, so those are my two components of R. Okay, so the 4.5 and 6.2. So now all I need to do is, I'm really hoping this grouped all together. Yeah, it did. Drag those over, and this is my actual diagram for R. That's what it's going to be. Where 4.5 is actually, it's not super clear, but it's the upwards part here. Okay, so just to go over my method, for every force that was acting on this object, I drew a force in the exact opposite direction with the same magnitude to cancel it out. Because equilibrium means it's not accelerating, there's no resultant force, there's no force acting on the system overall. Then all I did is I made a triangle out of them. Now if you notice, that gives me the direction, so it must be one of either this one or this one, up and to the right. Now all I need to do is work out the magnitude. Well, the magnitude is just going to be Pythagoras. Okay, so we have, again, a triangle with those lengths, and we're just trying to work out the third side. And R, if you remember, is just going to be 6.2 squared plus 4.5 squared. So again, with questions like this, it might seem fairly easy once you've practiced, right? It's not going to be easy for those of you seeing this for the first time, but for those of you that have seen this before, you might think it's quite easy. Bear in mind, a lot of students made a mistake on this question because they rushed. Okay, it's very easy for them to think R is a resultant force, for example, and they would have picked one of the ones that are going down. If you notice, the magnitude is the same for each pair, right? So you have one magnitude and two directions, another magnitude and two directions. They picked the wrong direction but got the right magnitude. So in this case, the right magnitude was 7.7 newtons, which means the row is A, the correct one, this one here. But they picked the bottom one, as in B, because they looked and they saw that the forces were going down and to the left, so they thought that would be the resultant force. That is the resultant force of those two, but R isn't a resultant force. It's the one that's making it in equilibrium. So they completely breezed over this word here, equilibrium, which means there's no resultant force, which means all forces are cancelled out with each other. Okay, so that's where the mistake was made. We have a very similar question from Edexcel. So a plane is travelling north at 42 meters per second, enters a region with wind blowing from the east at 7.5 meters per second. So to keep travelling straight up north, it turns towards the east without changing thrust. Okay, so again, if you imagine it, if you're going straight ahead and something hits you from the side, you're going to start moving this way. So to counteract that, you turn into that, so you can keep going in one straight line. And it says, which of the following can be used to calculate the angle through which the plane turns? Well, if you notice, the angle that it turns is just going to be this angle here. So if I draw this a bit more simply, we have the 7.5 acting this way, and with the 42 acting this way. So the angle through which I had to turn, remember, the plane at first was looking upwards, yeah? Now this is actually a really important thing. I'm going to work out this angle here, and that's going to give me my value for how far it has to turn, okay? Now, the two sides that I have are adjacent and hypotenuse. So to work out theta here, it's just rudimentary trigonometry. So theta should equal inverse cos 7.5 over 42. Right? The adjacent sides over the hypotenuse. So the question is, why is that not one of the answers here? Okay? So if you think about it, and this is where we have to be careful, that angle will give me theta over here. However, I'm actually looking for the direction that it turns, which would be this angle. How do I get that angle? Well, I do 90 minus inverse cos 7.5 over 42. Does that make sense? So again, with these 1 mark multiple choice questions, they look easy, but they're designed to trick you. So working out this angle is rudimentary, but working out the angle that it turns is a lot. It's not a lot harder. It's just that you need to realize that it was pointing north and it goes to this direction. So working out this inside angle It's just, you just need to do 90 minus it. Now, as you may know, the cos graph is just a translation of the sine graph. So this actually is the exact same as just doing inverse sine 7.5 over 42. Make sense? Because again, the cos graph is just 90 degrees ahead of the sine graph. So if you take away 90 from that, so it's the other way around. The cos graph is 90 degrees behind the sine graph. So if we're adding 90 to it, it's going to just become the sine graph. So it just looks like this. Okay. And lastly, we have a man is walking at a constant horizontal velocity of 1.2 meters per second. So let's draw that. In the rain. To the man, the rain appears to be falling vertically at a velocity of 1.8 meters per second. So like that. Okay? Now, here's the thing. The reason why this question is a bit weird and it's worth 5 marks is it takes a little bit of thinking, because when you're walking in the rain doesn't actually appear to be falling straight down. Right? It appears to be falling towards you. If you think about rain, if it's falling straight down, your face should never get wet, only your head. But as we all know, if we're walking in the rain hits us in the face. That's because we're walking into it, so it's as if we are standing still and the rain is moving towards us, when in actuality we're walking into the rain. This is a concept called relativity, which means that it's kind of indistinguishable which things are moving. So let's say if I was running at you at 20 meters per second, physically speaking, that is the same as you running towards me at 20 meters per second, or both of us running towards each other at 10 meters per second. It would appear the same to both of us. Now, of course, as human beings, you might think that's really weird because we have other points of reference, right? Because I can look, for example, I know I'm moving because I can see other buildings and stuff moving around me and I can feel my arms running. But if somehow you were in the cold vacuum of space, there's nothing around you, right? And I pushed, and you were pushed towards me at 20 meters per second, it would be the same, it would look the same as if I was moving towards you at 20 meters per second. So the only reason why we know that we're moving towards each other, which one of us is moving, is because we can see body parts moving, right? But in actuality, it doesn't matter. So, for it to appear that the rain is falling straight down, he must be walking in the same direction as the rain. That's why the question seems a bit weird, but to be honest, you don't actually need to know any of that. So we're trying to basically work out this resultant velocity here. And that's it. So yeah, it's a 5 mark question, but keep in mind you need to actually draw it to scale, which means let's say you wrote that 0.6 centimeters equals, 1 centimeter is 0.6 meters per second, then this top thing should be, then this top side should be 2 centimeters long, and this side should be 3 centimeters long. And then you need to be able to measure this third side in order to work out your value. I'm going to cheat quickly because I'm just going to use a formula instead, but it's the same concept. So again, even without actually knowing what I was talking about with in terms of relativity and all that fun stuff, you can still answer the question perfectly fine. Just use the maths. And you should measure it at 2.16, so technically we should give it to 2 significant figures or 1 decimal place, because everything else is given to 1 decimal place. Okay? But all they wanted you to really do is actually measure it afterwards. But again, that question kind of confused people because they put the arrows in the wrong directions and things like that. But this is completely fine and the correct answer. And I'll see you in the next one.